Hey everyone, welcome to another ChemPhys passage breakdown here. We're going to be talking about this methemoglobinemia passage today. There's going to be some nice information about metals, ions, bonding, all those kinds of things here, and we're hoping we can build some passage strategy with it too. The protocol here, I'm going to go over the passage itself. I'm going to go over the way that I break it down, and then we'll go through the questions. I'll talk about how I start reading the question stem and see how it turns out. So, to start, how do I, as a tutor, read chem phys passages, biochem passages, like social passages, anything but cars? Pretty much what I do, I always start with the passage first. I find that's much more natural for me and for most of my students, and it's questions first. If questions first works really well for you, then roll with it, right? But I find that most students who are undifferentiated, not sure yet to where to start, should go passage first. I'm going to say, is this passage just a fact passage where it tells me a bunch of things that are true and I have to reason from it? Or is it an experiment passage where we're told about some kind of experimental intervention that's done? We're told about data that are gathered, and we're asked to interpret those. We're asked to understand the methodology and maybe comment on ways it could be improved. This, we already see a figure, and I see that we have, what looks like a very experimental description here. So I always just skim first to say, is this experimental or is this fact-based? If it's fact-based, I just kind of read it, see if there's anything that really jumps out to me, and then go to the questions. The goal being that I kind of have a mental map of the passage. I know what information is contained in which paragraph, so that I don't need to scan the entire passage every time I need to look back. Here, though, I'm going to be looking more at the intentional division of the passage into three parts. Every experimental passage, with only a tiny few exceptions, is going to have an intro that's just facts, right? Things that are true. It's going to have some statement of research purpose, I like to call it, where we're basically saying, here is what the researchers are trying to accomplish with what they're about to carry out. And then they're going to have the methodology, the data, all the specifics of the experiment. So here, what we're going to do is we're going to divide this. We have a very clear statement of research purpose here. It's almost always going to come right before the discussion of the methodology and or data. And, there's usually going to be a like to do X or in order to accomplish X, researchers did Y. And in this case, you can see that very clearly here. So we have a very abbreviated depiction of the disease, our statement of research purpose, which we're going to use when we're interpreting the data later. We're going to make sure our data actually shed light on the purpose that the experimenters were trying to advance. And then we're going to look at the data themselves, read through it. So now that I've done all that, I can go top to bottom, and I know if there's going to be questions about just things that are generally true, I'm probably looking at this first paragraph. That's the only space with introduction. Okay. So we're told methemoglobinemia is a human disorder in which hemoglobin is present in 3 plus ferric state rather than the usual 2 plus. They give us a new term here. CP and especially BB love to do that, where they give you a new term and ask you to run with it, right? We're given our statement of research purpose, and we know that we're trying to see how the change from ferrous to ferric is going to affect the how the hemoglobin behaves. We're given some, and I encourage you to pause if you want to read ahead a little bit. I encourage you to pause and do so. I'll zoom out a little bit in my browser so you can see more of what's going on. But here, this is just know there's a little bit after this. But just to kind of go through it quickly, what I see here is that we have how the hemoglobin is turned into methemoglobin, which remember is our oxidized version. We see some details about our data, right? Excuse me, our methodology. Do I know what these terms mean here? No, I don't know what this SORA region is. I don't know what the relevance of circular dichromosome 2 is. I don't know that, right? We see this stuff about page, SDS page. Okay, so I know what a native page and SDS page are, but I know what reducing conditions are. The rest of this is probably just unfamiliar stuff that's there to throw me off my game. Very well. Then we start getting into data, the SORT region. A maximum absorptivity, right? There should be absorptivity here. Maximum absorptivity at 415 nanometers. And we see that the methemoglobin, right after being prepared, had a maximum that's a little different. I don't really know what this means. I know that this is related to the energy difference between molecular orbitals, but that doesn't really mean anything to me. That's just how UV-vis spectroscopy works. I see figure one, I see table one, so I'm just gonna say, okay, I have a vague idea what's going on. There's some difference here. right? And I don't know what it is yet. If I need to interpret it, I'm guessing a question stem will give me the information necessary. Like, say that he oxygen binding is strongly predicted by ability of hemoglobin to absorb the most possible UV light at 415 nanometers. I guess in this case it'd be visible light. But you get the idea. Like, since I don't know what that is and there's no content about it, it's not like SDS page where I'm expected to know what that is. I'm not going to worry about it. I see a figure in a table, so I'm going to apply my figure in table technique. Step one is just what are our variables, independent and dependent. Our independent variable here is really whether we have normal hemoglobin A or the oxidized methemoglobin form. You could argue that the wavelength is an independent variable, but that's really just how the spectrophotometer works. Our dependent variable is this motion of molar absorptivity. And I don't really know what that means, but it's just UV vis. I know how UV vis works generally. I know that different molecules will have different hits in different spots, and I know that this is generally used for things with conjugated bonds or other forms of delocalized electrons like that. Nothing you really need to worry about here. Step two, what is the relevance of each of these variables? Well, I kind of already talked about that, right? We talked about what molar absorptivity means. It just means there's a difference, right? There's some meaningful difference. Step three is to interpret, which we may or may not be ready to do, and we're going to interpret it in light of our statement of research purpose. It looks like methemoglobin does have some meaningful change to its structure. We have no information here on ligand binding ability. Okay. Then we're going to go down here, table one. I'll zoom in so we can see it a little better. Here we see that we have the following independent variables, whether we have normal HbA, fresh, or prolonged. What prolonged means is that we're basically just doing prolonged oxidization with the sodium nitrate. You may say, how do we get a lower char or a higher charge if we have reducing conditions? But we can imagine that this is going to be around for longer than the dithiothriatol, which you don't need to know what that is, but you're told what it is, so you need to run with it. So here we're given a SORAT maximum. Again, I don't know what that is. I don't need to. They're just trying to freak me out with unfamiliar terms. Alpha helical content, that's just some indication of how it's folded. Native page, they tell you what they're looking for, presence or absence of a tetramer, right? And then SDS page, they tell you some molecular weight in kilodaltons. Okay. Then finally, we have our Hemox analyzer deal here, and we see our independent variable is normal. Is it normal HbA, fresh methemoglobin, excuse me. Our the partial pressure of O2 is kind of an independent variable, but often the legends have them. And our dependent variable is fractional saturation, so basically what proportion of the binding sites for oxygen of hemoglobin or methemoglobin are actually occupied by oxygen. And what we see here, we see that, nice sigmoidal hemoglobin curve. And with methoxyhemoglobin, we see very little, maybe a tiny bit of cooperativity, but, not much there. Okay. Now, we were looking at reversibility. We have another statement of research purpose here, so we're going to keep that in mind. Reversibility, presumably, of the creation of the ferric methemoglobin from the ferrous. So we see ascorbic acid. You may recognize that as vitamin C. You don't really need to know that. And what we see is, after treatment, we seem to get both structural and functional indication of reversibility. But it looks like after prolonged nitrate exposure, we lose that reversibility. And we see loss of tetrameric species, maybe our quaternary structure is blown up in a way that vitamin C can't rescue. Now we get this little detail here, so I could coordinate with kinetic system from HbA. I'm just going to keep that in mind. There's probably going to be a question about it because it doesn't really tell us anything. So that takes us to question one. How do I know this? Oxidation states. We are told charges here, 3 plus and 2 plus. What is an oxidation state? It's just the charge if you assume that every bond is going to be completely ionic. What that means is, unless the elements taking part are exactly the same, whichever one is more electronegative is going to kind of win the bond. So each electron, unless it's a coordinate covalent bond, each atom in the pair is going to donate one electron, and then the winner, the more electronegative, is going to take both. So the idea is, what is the charge going to be? The idea of oxidation state is, what is the charge going to be if you take the charge that it has intrinsically, and then you add to it the contribution of giving up one electron to form the bond, and then either getting two back, getting one back if it's a tie, or getting zero back if you're bound to a more electronegative atom than yourself. So the nice thing about iron in hemoglobin, you're expected to vaguely remember the porphyrin ring. You're expected to remember that this is a structure where you have coordinate covalent bonds between an iron cation and a methemoglobin, or excuse me, a nitrogen in the heme. And as a coordinate covalent bond, the nitrogen donates both. Since nitrogen is way more electronegative than iron, it's going to take both back. But what that means is there's no contribution to your oxidation number. So the oxidation state is just the charge. And we see +2, +3. Very good. That works out perfectly. So for hemoglobin, we're told that the usual hemoglobin is +2 charge, and there's no non-coordinate covalent bonds. So we're just going to say that its oxidation state is its charge because there's no covalent bonds to consider that aren't coordinate, right? Yes, iron loses 2 electrons from the coordinate covalent bond, but it never actually donated any to begin with. So it got 2 from the nitrogen, loses it. It's a wash. And then the same is true for the methemoglobin because no new covalent bonds are made. There we go. Next question. What structural level of hemoglobin is most directly assessed by native page? So native page, we know we're only told 2 things about it. We have this little bit here, and we have native page here. And what they tell us in table 1 is that it's about whether there's a tetramer or not. As you know, a tetramer is a combination of 4 monomers, so that's quaternary structure through and through. We can go ahead with that. Secondary structure, remember, is side chain interactions. Tertiary structure involves at least, or excuse me, non-side chain, backbone interactions. That's secondary structure. Tertiary structure involves at least one side chain. Secondary, tertiary, and quaternary are all related to the 3D structure of the protein, but the idea is that the secondary kind of falls into place before the tertiary does, and then the tertiary kind of falls into place before the quaternary does, hence the different terms. Question 3. So we're asked about a knot, and we always highlight our knots because we don't want to miss them. Methemoglobin does not disrupt the overall fold within subunits. So we're not looking at tetramer changes in native page, right? Like that's only possible if you have intact usual bonding, but so be it, right? In contrast, what we see here, the sort band shift is just something we don't really know what that is. That's okay. You're going to be given things that you don't know the meaning of. That just happens. The alpha helical content, that implies roughly similar patterns of bonding. We can see we only go from 72 to 68. So that could mean that things are roughly similar. And the subunit molecular weight of 16 kilodaltons on SCS page. Well, molecular weight doesn't say anything about folding. It just means what amino acids do you have and how many. So I'm looking at answer choice B here. That looks the best, and life is good. Okay, question 4. Which conclusion about cooperativity is most consistent with figure 2? Remember, cooperativity, we're looking for that nice sigmoidal curve where we see significant cooperative binding. And here I see the hemoglobin has that nice sigmoidal, right? So it has a bulge out here, goes more vertical here, and then it has a bulge up here as it goes. That's a very sigmoidal, and that makes sense because the idea is it gets easier and easier to add more oxygen. The more oxygen's already there. Positive feedback loop, you could say. So hemoglobin A clearly has that cooperativity. Methemoglobin, maybe it has a little, but there's so little oxygen binding being done, I can't assess whether there's a good sigmoidal curve. So I don't really like answer choice B or answer choice C because there's too much of what's, discussion of methemoglobin having that. And then D, a hyperbolic HbA curve is going to look like this, where it just kind of rounds. It only has one bulge. It's in the one here and then one here. So a hyperbolic curve would look like that. That's like myoglobin. That's not what we have here. So I like A the best because it correctly says that the methoxyhemoglobin has methemoglobin has no significant cooperativity. Okay. Question 5. Okay, cyanide can coordinate to MetHB ion. We remind ourselves what's going down here. We don't really get any information here. In forming the cyanide methemoglobin complex, which species donates the electron pair that creates the coordinate covalent bond? Oh, we talked about this, right? So basically the idea is your ligand is going to be something highly electronegative, like a negatively charged carbon that has, or excuse me, it's going to have lots of excess electron density. So it's usually an anion, right? That's going to donate the electrons because electrons are negative charge. So if you're positively charged, you're deprived of electrons, you're unlikely to be able to, well, donate electrons. So the cyanide ion is going to be pretty persuasive here as the source of that. The ferric ion is 3 plus. It's already highly electron deprived. Where is it going to donate electrons from? Molecular oxygen. That, we're not told anything about cyanide working intermediate through molecular oxygen. And proximal histidine side chain, histidine's positively charged. Again, positively charged things tend not to donate electrons because they're electron deprived. They're negative deprived. They're positive. Send that forward. All right, question 6. So we're told fetal hemoglobin has gamma subunits which do a histidine to serine. So basically, we're taking a positively charged amino acid and we're turning it into a polar but non-charged one. So chances are we're going to be eliminating a salt bridge here, or we're going to be creating a new salt bridge, positive, positive, or positive, negative, that causes a different state of mind. Or excuse me, I guess you wouldn't be doing that because serine is going to be unable to form a salt bridge. So we're probably going to be getting rid of a salt bridge, is the idea. Either we're going to be getting rid of a positive, positive repulsion, or we're going to be getting rid of a positive, negative attraction. Whatever it is, it's going to probably change things. So, when we look at something like D, that's not what histidine is. We can eliminate that. C, disrupting the proximal histidine coordination to heme iron. Again, histidine is positively charged. We're not expecting it to donate electrons. B, introducing a disulfide bond that increases oxygen affinity. That would be if this were cysteine and not serine, maybe. But here, 2,3 bisphosphoglycerate, you just have to know that that has a negative charge because it's bisphosphoglycerate. You should know the name of it. You should know what 2,3 BPG is. That's how you know what we're looking for here. So the idea is you should know that this is negatively charged because it's a phosphoglycerate. Phosphate groups are generally negative charge. Glycerate, it's an 8 ATE at the end. That's our nomenclature. And we're eliminating a positive charge. Question 7. In our heme group, we have coordination between iron and 4 nitrogen atoms. This one's a little bit of a review, but because a lot of students are a little bit weak on coordinate covalent bonds, it's a relatively niche topic. We wanted to give another introduction to it here. So basically, if we remember what's going on, whenever you see coordination, this is just coordinate covalent bonding. Again, it's tempting to say ionic bonding, but the nitrogens are not anions. They behave like anions, but if they were anions, they would just have a purely ionic bond. This is a coordinate covalent bond, which is a little bit different. So the idea being that you donate electrons and still share them with the target, the iron cation, but it's not as generous, not as equal as a typical covalent bond, which is one each and then shared. Hydrogen bonding between iron. Iron does not hydrogen bond. It's just nitrogen, oxygen, fluorine, pretty much. Hydrogen is bound to that. And the metallic bonding delocalized, that's what you see in a straight metal. So we're not expecting that. All right, and last question here. We see the ascorbic acid reversibility test. And what we see is that measurements were performed in a reducing buffer. Now, though, what we don't know is we went from 3 plus to 2 plus. That's a reduction in oxidation state. That's a reduction. So we don't actually know whether the ascorbic acid did it rather than the buffer. So to figure that out, we need to say, okay, well, ascorbic acid and the buffer are both there. We need to get rid of one and look at the other. So if A would let us see if the buffer on its own would do the job. B would tell us we're if ascorbic acid alone, but it's not rescuing anything. It's the already rescued hemoglobin A. So I don't like that. C, this is just going to denature it. I don't know what that's going to do to isolate any effect from the buffer. And then D, free heme, not bound to globin. Again, we don't know whether that's the area of denaturation or not. So there's too many other moving parts. I like A. So, I hope this passage was a little bit clear. Hope it helped clear up the coordinate covalent bond concept that a lot of students trip up on. We'll be happy to answer any questions you may have. Otherwise, well done, and keep hanging in there.